Hello and welcome to this final project presentation for our course in CSE 90 Cloud Computing taken at Harvard University Extension School. The project title was AWS Redshift. This project was undertaken to highlight key benefits and features of AWS Redshift and demonstrate how to create a data warehouse based on star schema, load some sample data, and run some sample queries. Redshift is Amazon's fully managed data warehouse in the cloud offering. Is based on acting parallel technology effect having roots in PostgreSQL. The service utilizes massively parallel processing, columnar storage, and data compression principles to enhance query performance. So why is AWS Redshift named so? Here's what James Byers, Wikispace's co-founder, said in March 15, 2013. Physics phenomenon aside, the name could be interpreted as a dig at Oracle, who heavily use the color red in marketing their database products. The main uses, benefits, and drawbacks and challenges. The main uses being Redshift is primarily used for data warehouse services in the cloud for elastic demand of data size ranging from hundreds of gigabytes to petabytes and more. Benefits: the service is very fast and highly scalable. It's cost effective with no long-term commitments. It's very simple and easy to use. It's fault tolerant to replication of data. It has end-to-end security and has auditable API calls and SQL operations. There are options for on-premises key management, and which is some of the key benefits of Redshift. The drawbacks of the service does not provide an enforcement on primary key constraints, with the drawback that some data can be loaded to the database multiple times, thereby distorting query results. This must be enforced at a SQL application level. The challenges are transferring terabyte to petabyte scale of data reliably from local machine to Redshift cluster, while loading multiple records can be fast. However, a single record entry can be very time consuming. Benefits and features, and once again, it is pretty fast and scalable. The data warehouse is designed and optimized to provide fast query performance on data size that can scale from a few hundred gigabyte to petabyte. It's cost effective and there are no strings attached. With no upfront cost of contracts and the usage of pay-per-use model, the rates can range from 25 cents an hour for 160 gig or to 85 cents an hour for 2 terabytes. The rate can go down even to 10 cents per hour, or even to, and which makes to $5,500 per terabyte per year, or 22.3 about 0.3 cents per terabyte per hour, which makes it about $1,000 per terabyte per year. Very simple and easy to use, and the system is very fault tolerant. Remarkably simple. It allows a cluster to be created within minutes and with only a few clicks. All data warehouse administration and management is handled by Redshift and allows easy adding and removing computing nodes from clusters to meet elasticity of demands. The system provides fault tolerance to replication and regular automated backups in S3 buckets and restoration using snapshots. The security is pretty comprehensive, providing with the audit trail facility. There is the sign-in credentials that provides access to Redshift console through only AWS account privileges. Access to specific Amazon Redshift resources is controlled through user-defined IAM accounts. The users are the one who define the cluster security group. Users can also launch their clusters in a virtual private cloud, and the cluster and the encryption can be at the cluster level to ensure all data and user-created tables are encrypted. Users can use SSL to encrypt connection to the cluster. And they can use either server-side or client-side encryption while loading data to S3. For server-side encryption, Amazon S3 handles decryption transparently, but for client-side encryption, Redshift copy command decrypts the data as it loads the table. Data in transit. To protect data in transit within AWS Cloud, Amazon Redshift uses hardware-accelerated SSL to communicate with Amazon S3 or DynamoDB, copy and load backup and restore operations. Redshift uses industry-standard SQL and JDBC ODBC connections and PostgreSQL drivers. It is integrated with other AWS services, and data can be loaded in parallel to each node from S3, DynamoDB, EC2, or even on-premise servers using SSH, Data Pipeline, and Amazon Kinesis. The architecture that supports massively parallel processing for faster query performance has a cluster at the heart. The cluster is made up of vast array of computing nodes which are connected to leader nodes. The SQL client applications connects to this leader node to JDBC or ODBC drivers. They don't have any direct access to the compute nodes. And the nodes are made up of multi-core processors. Each core is known as a slice. These nodes are connected to high-speed networks with Amazon custom protocols, and the databases reside in these compute nodes. The internal architecture and system operation shows that the leader node manages the communication with the external SQL client, and it manages and coordinates the compute codes. It parses and develops query execution plan. It compiles and distributes compiled codes to compute nodes. It allocates the data to compute nodes. And the compute node in turn will receive and execute the compiled code and will send intermediate results to leader node for aggregation. For efficient data storage, Redshift uses columnar data storage, which is suitable for OLAP, whereas typically for OLTP transactions, data is stored in row-wise in blocks. So they are stored in sequence in blocks, because for OLTP transactions, almost every field is used for updates. But for OLAP, when you're querying a database for read-only purpose, you pick only few columns out of like 30, 40, even 100 columns. That makes more sense to put the columns in sequence instead of the rows. So this will reduce the disk I/O operations, and the data loads to memory, and therefore it will free up the memory for increased in-memory processing. So this lends to optimizing analytical query performance. And with the appropriate sorting of the column, the query processor can rapidly filter out a large subset of data blocks. So in order to demonstrate the basic features of Redshift, basically you have to go through 5 steps to create a data warehouse in Redshift. You first launch a cluster of nodes. You provision the cluster. You connect to the cluster and create the data tables in the cluster. Upload the data and perform data analysis queries. In our case, we used a sample data publicly available in S3 bucket. That data is basically sales transaction data of series of events stored in 2 fact tables and 5 dimension tables. The 2 fact tables contains less than 200,000 rows, and dimensions range from 11 rows in category table and up to 50,000 rows in the users table. Okay, to start the demo, we have to prepare we have to download and install some drivers and tools. So we need to download the SQL client drivers and tools from this site. This will require Java runtime 7 minimum. I downloaded generic package from this site. Then you have to install into the tool following instruction here. And also download the JDBC driver version 8 from here. And we have to determine the firewall rules in the local machine and also the cluster, allowing access on port 5439. We have to ensure that 5439 is open in both the local machine as well as the cluster. So in step 2.1, we log into AWS console, and when we do that, I selected my region to be US East, and that brings up the AWS console, and we select Redshift. When you click Redshift, you get to this screen. You will select cluster here, and then click launch cluster. That's all. This brings you to here. Here we provide the cluster details, name the cluster, give the port name to be open, database port, the master username, and the passwords. And click continue. This will bring to the next screen. Here we do some node configuration, the compute code notification. We pick up DW2 large and leave everything else as default. And I picked single node, which means my leader node and my compute node are the same. Press continue. Brings you to the more configuration. Basically, we leave whatever is in default. Then ensure that an availability zone I picked at US East 1A, and the security group I picked default. So it allows me to add the inbound rules later. And before we launch, we review the configuration, ensure that port 5431 is designated to the database port. And since I did not enable any CloudWatch alarms, it shows that alarms will not be created, which is okay. And once we click OK, the cluster is launched, and to verify whether it is launched, we just check the cluster status to be available and the DB health healthy. At this point, the cluster is up and running. Now we go back to the cluster list. We click on My Cluster, and this will bring me to this screen. Then I click here to get to this screen, and I click on Inbound tab and click Edit, and there I will enter the custom TCP rule at the port 5439 and the source to be 000 from anywhere, and click Save, and this will be the result. Also, from my cluster details, I'll go to the JDBC URL and copy this URL from there, because this is the one that I will use to connect. So I go to SQL Workbench. That should be up and running, and I click on the connection, and this will bring up to the screen here. In the URL table, in the URL text box, I paste that JDBC URL I picked up from the cluster and select auto commit and leave the other ones as default. Do nothing else here. And of course, my username is master user, and the password to be the same as I used for the cluster. And I click OK, and I should be connected. And if the connection is successful, to verify that, I go to statement 1 of the SQL Workbench tool, and I type this select query current user, and it shows me the master user is the current user, which shows that I am connected to the cluster. I then go back to my workbench again and then start creating the tables using these create table queries. There are about 7 of them over here. I'm just showing one. And once I've created the query, I go down and I do the copying of the data from S3 bucket. This is the address for the S3 bucket. I provide my credentials, my access key, my secret key, and the delimiter. This was a tab. This is the delimiter was used, and then it will copy the data from the S3 bucket to the cluster. And this is the result of the successful execution. In step 6, we run some queries now. We try to get the definition of the sales table by simply saying select star from pg underscore table def, where table name equals to sales, and this is what we get. We find total sales by giving this query, select sum to quantity sold from sales to table sales and date. We join them, give a calendar date, and this is the result we get, 210. Same thing, we try to find the top 10 buyers by quantity. We do a select buyer ID from so and so from sales, group by ID, and where buyer ID, user ID, and so on. And this is the top 10 buyers by quantity. We find events in 99.9 percentile in terms of all-time gross sales, and this is the query we provide, and the results is here. This is all in the SQL Workbench. And then we try to find the top 5 sellers in San Diego. This is the query we give, and this is the result. This is directly querying the star schema database. We're not using any cubes or data marts here. You can also view the queries in the Redshift console. We go to the console, click on the cluster list and click on My Cluster and click on the query thread, and it will show you the queries that you've run and their status completed. So you can also look at pick up any of the query up there. So let's say you pick 411 from here, and that will show you the query itself, what was the query, and the explain plan, how the query was, execution plan of the query. And if you want to show the data load that we did from S3 to the cluster, you can also see the status in this window. You have to click on the load tab to see this. And if you want to monitor the performance, you can look at the CPU utilization, the network throughput. You can just click on the performance tab and it will give you the CPU utilization, network receive throughput. You can look at the read-write IOPS, and also you can look at the write latency, read throughput. You can also see the database connections, the health status, and the disk percentage. You see very low data has been stored in the physical disk here. And that's about it. I hope you've enjoyed this presentation, and thank you for watching.